Hello, welcome back again. So this is still continuing the IEEE Cyber Science 2020 conference, Monday, June 15, 2020, session 1, track 1, focusing on critical national infrastructures and CERTs. So the next presentation is titled Vulnerability-Based Impact Criticality Estimation for Industrial Control System. And that's going to be presented by one of the authors, Uchenna Daniel Ani. So with that, can I hand over to Uchenna to present his research? Thank you.
Thank you very much, Cyril. Just a little check-in to be sure everyone is, can you hear me? Hello?
Yes, yeah, we can hear you.
Thank you. So thank you very much again, Cyril, for having me as a presenter in this conference, and then for an opportunity to present part of the work we are doing in this space. So I'm making the presentation on behalf of the team. My name is Uchenna Ani from University College London. And my colleagues in this work are, there's Dr. Hongmei from Cranfield University and Professor Tiwari from the University of Sheffield. So the talk I'll be giving today is about vulnerability-based impact criticality estimation for industrial control systems. And just a quick run through of what we intend to cover even in this presentation. So we're going to have a little bit of an understanding of the space, the background. I guess quite a number of us have a good understanding about this. And then we will look at the approach, the model we are proposing to address the issue we have, one of the issues we have come across. And then we'll look at how we went about testing and validating or evaluating what we presented, and then some couple of conclusions and future work, because it is a work that is in progress. Yeah, so a little bit of background. So we all know what Industry 4.0 is, and we know that everything within the industry now is getting digitalized, a lot of connectivity. So basically we see Industry 4.0 as growing with a level of an unprecedented development. So there is this increase in scale, the speed and complexity. So these are three key factors we've seen that is driving the industrial revolution, moving on from Industry 1.0 to where we are at the moment. And typically where we are at the moment defines an industrial control system trend whereby we see a level of integration between the IT and the OT. So the IT is a information technology enterprise space and infrastructure component thereby. And then the OT is the operational technology space or protocols and as well as an infrastructure as well. So Industrial 4.0 is enabling these two areas to come together. So we see systems now being developed where there are IT and OT components within the network. And the essence of this has always been to drive performance, the desire to increase performance, the desire to increase productivity. While this does promise to improve this or provide these benefits of performance and productivity, we also note that a couple of security issues have been enabled as a result of this integration. And so there is the typical instances of most of the IT devices that are on these platforms, on these networks, are weakly configured for security. And then we also have the OT infrastructure, which were initially designed without security in mind, now coming into the system. So they now belong to a network, and yet they don't have very much security in them. And then these two features have come to enable some significant level of attack surface. So this has broadened the attack surface. And we will see that the broadening this kind of development within the industrial environment, we will see that the attacks are very feasible, because we will see that we will see from trends and from the reports of incidences that much of the attacks that target this kind of infrastructure have got very significant impacts. And these impacts can be physical, they could be reputational, they could be economic, and they could be environmental as well, as we see in the case of the German steel mill cyber attack that actually caused a massive explosion. So we can imagine the kind of physical or safety risks that would have posed to the people around there. We also observe that as a result of these attacks, then there are a level of interdependencies between most of these critical infrastructures, because we've got ICSs, and these ICSs are typically used to control this kind of critical infrastructure. So we see dependencies that ensures that an impact on one system tends to ripple down onto another system, and so the impacts actually flow. And so we then thought about there is a need then in this kind of scenario for security, and most especially again for safety, which is necessary in order to minimize the failures and the impacts. Yeah, so we see that these high vulnerabilities could be the most vulnerable point. So high impact vulnerabilities could actually mean the point where there is the greatest vulnerability within the system. And we also, we note that this most vulnerable point could also be referred to as the potential weak links within the system. In security now, there is this very popular talk that is, the security of a system is as weak or is as strong as its weakest link. So if you find the weakest link, then you're able to exploit, and you're able to exert a maximum level of attack within the system. So going on forward, in order to be most typically in most of the systems and in the industry, typically one of the ways that this vulnerabilities and these impacts tend to be managed is through vulnerability analysis. And one of the common schemes out there that supports vulnerability analysis is CVSS. That's a common vulnerability assessment scheme or scoring system, which came about, which was established by the Forum for Incident Response and Security Teams. So this is an open vulnerability standard that helps to support the assessment of vulnerabilities, and is built on the popular CIA traits like the confidentiality, the integrity, and the availability of characteristics within the system. Now, this CVSS helps to prioritize responses, and then to also control the application of, in order to also to provide, also to control resources according to the threat levels within the system. However, we have also seen that CVSS, regardless of its use, I mean, despite how useful it is, also has some couple of limitations. One is that it reflects technical exploitability. So what it basically does, that it doesn't really talk about the very specifics of the system, but it only presents the exploitability of a system or a vulnerability based on the general understanding of that vulnerability, not in relation to the very specifics of the environment in question. And so because of that, it doesn't really reflect potential impacts or the actual likelihood of exploiting that system. It just gives you a fair understanding of what this might be. So we, as a result of that, most times this tend to be one of the approaches that is used to address vulnerabilities or to fix. Most industries used to address security problems and to provide controls. But we think that there are limitations or issues related to that approach. That is because it often brings about inaccurate reflections of the actual severities of a vulnerability. And then there is a case whereby when you go through that process, you come across so very many vulnerabilities that are within the system, a large chunk of them, and then you often have to go through the process of deciding which of these vulnerabilities is most impacting, which is most critical, and how do you go about prioritizing which vulnerabilities to address first, given the resources you have. So that's the basic part of the work that this paper seeks to address, just to find a way to provide a way to understand these vulnerabilities in terms of their criticality and how much they can impact the entire system, and then to use that as a basis to prioritize control given the kind of resources that may be available. So quickly, So this is what we have. So we proposed this method that is based on CVSS still. So it builds upon CVSS, and it's a multi-attribute vulnerability-based analysis. So we, rather than just focusing on the CVSS, our approach explores a little more other attributes that relate to the CVSS. So moving forward, we also want the approach considers a couple of other factors and a couple of other characteristics. And so we look at the multiple and the dynamic attributes of the vulnerabilities with respect or in relations to the immediate environment, so the immediate network and how the network is set up as well. And then that helps us, or that can help to gain a better view of the impact, as well as to resolve any kind of uncertainties that may abound as a result of maybe having multiple vulnerabilities or even similar multiple vulnerabilities in this case. So MAFCA uses an index, so it's a probability approach. And then it is also a quantitative approach that helps us to do that and to guide the ranking and the prioritization of controls. So there are basically 3 steps that drives us to doing this. So the first has to do with, if you look at it from the diagram we've got there, so drawing from a vulnerability enumeration, so process where you've got vulnerability analysis, whatever tool that you use that is maybe used to do that, you're able to aggregate a number of vulnerabilities, but these vulnerabilities are base vulnerabilities. So in this case, we look at them as base scores, just typically as it comes in terms of CVSS analysis. And then, but then from the base score, you are able to abstract and dig a little further to come about the temporal scores and the environmental scores. Now, these scores are still coming from CVSS. And then because these scores at this level do not speak much about the environment in question, it becomes necessary to look at some other characteristics that speak about the environment. And so we propose looking at attack probability enumeration, and then we also look at functional dependency as a process. So the first stage of doing this evaluation, that's the point we call vulnerability exploit potential, is a process of combining the probability of attack. Now, this probability of attack is with respect to the network, the architecture in question that is being evaluated, and then combining that with a temporal severity ratio or temporal severity index that can be evaluated from the CVSS guide, and that is contained in the CVSS guide. So we've got a couple of, the model we have combines a couple of quantitative approaches, formulas for this. So we look at the probability of attack with respect to the components, and then considering the cases of multiple occurrences of that vulnerability in the evaluation of that probability. So, and then on the other side, we combine, in order to understand the vulnerability impact, which is the next point. I just want to rush this quickly, and then so that we would have time for questions. And then the other part of it is the vulnerability impact potential. In this case, we look at the environmental severity, also drawn from CVSS, rather than just using the base score. We move deeper down into using the environmental score. And this is combined with what we call the functional dependency index. So this factors in the idea of functional dependency analysis. So where we look at the impacts, the relationship or the dependency of functions within a network, how much a device depends on another device connected to it. So what it actually means is that potentially when there is an attack that alters the functionality of a system or a particular component within the network, we want to understand how much does that impact on that one targeted component influence or affect the functionalities of other components within the system. And so we evaluate that again through functional dependency analysis. So in order to understand functional dependency, we look at it from using a switch function that indicates whether there is a connection to a particular device or whether there is not a connection, and then that sums up continually. And so that gives us an understanding, or that can help to give us an understanding of what the vulnerability impact is. So at this point, we've got vulnerability exploit potential. That is what is possible to be done. But then we look at the impact, again, what will be the consequence of this possibility. So those are the two things we have explored, and we looked at it, and then we believe that looking at this, combining these parameters is likely to give a more profound view of what the impact of a vulnerability, or the severity of a vulnerability is within a network. So we move down further to use that. Sorry, so the last bit is estimating criticality, whereby we're able to combine the vulnerability impact and the vulnerability exploit potential in order to arrive at what we call the criticality index. And so that criticality index helps to define, I mean, the weight of each of the vulnerabilities with respect to its external attributes as contained within public domain, as well as its environmental internal attributes as regards to the network within which that vulnerability exists. And that leads us to equation 14, which just provides a ranking, or a process of just ordering these vulnerabilities to identify which one needs to be addressed first based on the resources. And given that organizations might not have all of the resources, they may not have all the resources to address every security problem all at the same time. And so to test this, we did some emulation, so some modeling and simulation, and we used the test an emulator setup, a test bed that comprised both real hardwares and then some toy devices that are field devices. So we had the PLC, we have the input and output modules, the HMI, and the control applications. Now, these were real applications or real components that are used within the industrial environment for processing, for process control. And then in terms of IT, we had the network router, the network cables, and the workstation. Now, these are typical IT components as well. Then in the field device, we now had a 3D robot and a conveyor belt system. So these are toy devices that are often used for experiments like this. And so these were configured with the help of other experts in this area of process engineering to help in designing the process that was required, which involves actuating items or picking the items, dropping the item on the conveyor belt system and getting the conveyor belt system sensor to detect the presence of this item and then actuate a movement process to the place where it needs to be worked upon via a puncher. So the HMI was configured to monitor these processes and to either initiate a start or a stop at any point as desirable. So we had a running network system for this experiment, and like I said, it is still work in progress. We are still exploring other parts of this. However, in order to test this and the process and to test the approach we came up with, we had to use typical vulnerability analysis tool. So Nextbus was used, and this is an open source tool that you can get out there, and that was installed on a laptop. And so with this, we're able to connect that to the network, the test bed network, and then do a typical vulnerability analysis. Now that process helps us to obtain initial base scores of then CVSS base scores in this case. And so then we applied the process like I have mentioned much earlier, described in the earlier slide, the MAFCA evaluation process. And so in doing all of that, so that process involved evaluating the exploit potential, the vulnerability exploit potential, as well as the vulnerability impact potential, and then combining that using the model that we have proposed to actually do this. So we came up, the result is as follows. We came up with our 11 vulnerabilities, and these vulnerabilities were reflected in different parts. One of the key things we also found out was there were multiple vulnerabilities within single component. So for example, within the RTU, that's the control device. In this case, it was a PLC. We had that there are two vulnerabilities from there within the router, which is basically IT in this case. There were 4 vulnerabilities. The workstation that stood in there as a control workstation, it had a Windows operating system. So we also found that there were 2 vulnerabilities. So that's one of the things we found. The other bit we also found was that there were also the same vulnerabilities in multiple components, which is typically what you find each time you apply these processes within large scale industry where you've got so many components working together. So we had multiple vulnerabilities. For example, the same vulnerability was in the router. It was also on the RTU, and it was also on the RTU slave, both the master and the slave controllers. We also found similar vulnerabilities as we have there. Now, one of the key challenges then that our work wants to address is the issue of having the same vulnerabilities actually mean that this vulnerability means that you have the same base scores from the vulnerability analysis. And so one of the challenges then will be, it becomes to be very unclear which of these vulnerabilities has the greatest impact on the ICS network and how to apply controls to achieve the highest possible security control per time as this is applied. And so we'll see. Now, we also noted that there are variations in the BS. So BS is a base score, TS is a temporal score, and ES is their environmental score. If we look at the table, we will see that from table A, the one that is highlighted a little bit of red and amber, we see that the base scores are highlighted there, and the first 3, K1, K2, K3, had the same base score. And so if we had a bigger network, the possibility is there that there are going to be other devices that will have the same vulnerability. So we will have a problem of, well, in terms of the resources we have, how do we go about applying the best control that maximizes our results, given the resources we've got? And then if you look down, because of this kind of issue, we applied the model, and then it gave us the results we've got in the second table, that is table B, where we've got the TS, which is a temporal score. So rather than the typical 10.0, which is the maximum score you have in the base score for CVSS scores typically, we've got that this has actually come down to 9.1 because we, at this point, started considering some other attributes that are more connected to the real environment as opposed to just the general attributes that are known about the vulnerability, that is external attributes. And so to get it a ratio, because we had 0.91 for each of these as well, because now we have to put it on a ratio of in relation to the maximum that is feasible, which is 10.0. And the same thing applies when we did this, and we also had we had the environmental score as well as in evaluating the functional dependency. So based on this, as well as also evaluating the probability of attack. So one of the things we saw in the end of all of this is, rather than working with the base score, in terms of the environmental score, we see that K4, for example, has the highest severity of 9.7. And then it has, 9.7. And this indicated the vulnerability that, an SNP credential transmitted in clear text on the router. So what this basically means is that this can actually be subject easily to man-in-the-middle attack if a potential person wanted to exploit this. But so we will, one of the highlighted point is K4. And we see that even though this is the case here, we see that the environmental score is much, much higher than what we had on the temporal score. So in this case, it gives us a fairer understanding that considering the environmental score even gives us a better understanding of the impacts of these vulnerabilities. And so based on that, we looked at, we tried to, this is a representation of what we found out in all of this. One is that we see that higher vulnerability potential suggests higher likelihoods of being targeted. And then we also see that higher impacts suggest a potentially higher impact consequence. Now, the key things that we want to bring out is the ones highlighted in red. And though we said higher exploit potentials does not always suggest higher impacts. And this can be seen in the graph, the first graph where we have graph A, we will see that there is the dotted one is the vulnerability exploit potential, and the block lines are the vulnerability impact potential. We would actually notice that there is a difference between what happens, because in the case of vulnerability K2, K3, K6, their impact potentials, their vulnerability potentials was actually high, but then the impact potentials was lower. So it makes sense to see, okay, well, even this is the case, so we understand what this means in the context of our own environment. And then we also see that higher impact potentials does not always suggest most critical vulnerability and topmost priority. So this we can also see in the B part. If we superimpose the graph of B upon A, what we will discover is that this vulnerability K1, K1 in the first instance has a higher impact potential of 0.95, and then the criticality impact of 0.83. Then K4 has 0.97. So ordinarily, we would believe that K4 should have a higher criticality impact, but then we'll see that when we look at it in terms of impact, because of where K3 is resident on the network and how easy it is to be reached, then it means that K1 appears to even have a higher criticality impact. So this helps to really understand that there are a lot more details that need to be considered in terms of addressing this kind of issues within control environments, where there are possibility of this having very large vulnerability. So in conclusion, and then in summary before concluding, security risks are real within industrial environment, okay? And we think that a way to assess vulnerabilities and to prioritize them is something that is really very much needed in this time. Based on our thought is that on the minimum scale, environmental scores of vulnerabilities should be used at the minimum for resolving security management uncertainties like this, as we have described. And our model has shown that it is possible to have this and to be able to address this in this. So we think that using our model to drive decision-making on technical vulnerability management can really support optimizing control actions per response on applications. And that way, it's a way of trying to say that we're trying to support fixing the component weak links within a network. So MAVCA provides this, even the metrics with our model, we're able to provide a couple of other metrics that can actually be thought about and considered even in a large scale or even a broader security risk management system. Now, this is an ongoing work we're doing, and that's for a future work, we are looking at exploring this even further to a more socio-technical dimensions where we're able to analyze these vulnerabilities and estimate their potential impacts, considering both the technology vulnerability attributes as well as the social attributes, more typically the human attributes that also translate to vulnerabilities. We're also working on this tool and towards developing it into an automated process, bearing in mind the various tasks and the work that will be required to do the process as it is. So at this point, let me stop here, and I hope I have not overshot time, but then I'm happy to take any questions. Thank you very much.
Thanks, Uchenna. Daniel, that was really in-depth, very good presentation. Thank you very much. We've got a number of questions. The good thing is we have break after your talk. So even if we encroach 2 to 5 minutes into that, I hope that our audience don't mind. So we go through the first one. It says, can you explain the method you use to combine the probabilities? Are you using Bayesian probability or something else in your calculation?
Yeah, so we did not at this stage, we didn't use Bayesian network, Bayesian probability. So we didn't do this. Rather, we just considered it from the aspect of just the attack path analysis, whereby we look at the reachability of this. We looked at the occurrence of the vulnerabilities, and then we look at the reachability of this from each point of the network. So basically, it's just attack path analysis. So, but then we have identified, and you are right, the possibility of getting this may even improve further in terms of automation. That's why I talked about the automation part. Then we want to extend this further in terms of that part of Bayesian probability. Yes, that's a place we have recognized.
Thank you very much. The other question here says, how do you determine the parameters that you use for your measurements in each of the devices? So if you look at where you had your test bed, you had a router, you had an ICS, industrial control systems, and you associated parameters to those. So the question is, how did you determine those parameters against each device?
So when you say one, sorry, can you explain in terms of the parameters?
Yeah, so assigned to each device. So you had your K1, K2, K3.
Yeah, so K1, K2, K3 is just defining the vulnerabilities, not the devices themselves. It's the vulnerabilities on each device. So we didn't bother much. The only point at which the devices became relevant was at the point of evaluating functional dependency. But in terms of K1, K2, K3, we're just defining, using K1 as a variable to define a particular vulnerability that was found on a network. So when we were doing the evaluation, we focused on the vulnerabilities and how they link up. And then we just consider those devices as host devices for the vulnerabilities.
All right, thank you very much. So in terms of, you did say, you gave us some recommendations. So one of those that stems out is, how do you distinguish between vulnerability exploit potential and the actual vulnerability impact?
Yes, so if we go back to the photo, the graph, or let's say the image, the figure I presented. So vulnerability exploit potential in this case just gives an idea of what is feasible to be done as a malicious act in terms of the reachability of that device, okay, within the network. However, at that point, vulnerability potential just restricts an understanding of that vulnerability with respect to the device and the harm that is possible to that device. But then when we talk about the impact, it now takes it a little further. So vulnerability impact potential considers not only the device, but now how does this impact that is possible? I mean, how does this attack or this influence on the device? Now, how does it translate? How does it affect all other possible devices that may be relying on the functionality of this device? So that is where we talk about impact of functional dependency. So we evaluated functional dependency. So we did functional dependency analysis for the impact here.
Thank you. So for your future work, since this is a test bed, do you plan to test it in an enterprise network or test it in a real network, not just on a test bed? What's your future plan, future work plans?
Yeah, so part of our future plan is to actually test this within a real environment. It will make more sense to have this within a real environment where we've got both group of infrastructure, both IT and the OT, because that's the key thing there. So we are actually working at the moment with collaborators within this industry, but you would also agree with me how difficult it is to get people to allow you access to their network in this kind of research, except you have high level authorizations from above. And so that's one of the challenges we're struggling to cross at the moment, and we're really getting there. So we've got a couple of contacts within the rail industry who are now happy who we've started talking with, and hopefully we can take it off from there.